In this example, we have a 115-gram metal cylinder that you suspect is aluminum. You heat it to 80 degrees and then immerse it in a calorimeter containing 250 grams of water, initially at 20 degrees Celsius. The final temperature is 25.4 degrees Celsius. Is the material aluminum? So we have here a calorimeter. Like we said, it's a container containing water and insulated essentially. It's closed. And we heat up the aluminum and dip it in this water. Water initial was 20 degrees Celsius. And the hot cylinder it was at 80 degrees Celsius. So T of the cylinder initial is 80 degrees Celsius. The mass of the cylinder is 115 grams. And the mass of the water is 250 grams. I will dip the cylinder into the water and thus, so that's what we do, we mix the cylinder. Usually the calorimeter has a small opening for a thread so that we can place the cylinder inside and hang it in the middle and ensure some uniform distribution of heat. So we mix these two together and T final is 25.4 degrees Celsius. This is basically the temperature of both the cylinder and the water. We want to see if the material is indeed aluminum. How can we tell so? We should simply look for the specific heat and see if it satisfies the value of aluminum from the table of constants. Because like we said, the specific heat is a property of materials. So if I find the specific heat and it turns out to match that of aluminum, then yes, this material is indeed aluminum. So I'm just gonna check the transfer of heat. We start by saying that Q gained by water must be equal to minus Q lost by the cylinder. Whatever the hot cylinder is losing, any energy it loses will go to the water. By the way, sometimes the container itself will also heat up, not just the water. So the heat is also transferred to the container. In that case, you will clearly be given details about the container, and then you would know that you should involve it as well. I think we solved something on that last time. Yes, here it is. I told you the calorimeter is made of 0.15 kilograms of aluminum and contains 0.2 kilograms of water. These are the water and the cup. And then a mass is heated and added into the calorimeter. So here, the container will also take some heat, especially that it's aluminum, it's a metal, so metals usually heat up. So when I studied Q gained, I put the mass of the water and the mass of the cup. And when I studied Q lost, that was the sample of unknown material, of course. But if you're not given details about the cup, a calorimeter can be made of styrofoam, which does not take any heat. It's a weak conductor of heat, so it will not really heat up. It will not take any of the energy. It's not involved in the energy exchange. So if you're not given details about the container, we will assume it does not take any heat in the exchange that's happening. So I'll just put Q of water equals minus Q of the cylinder, and I'll just proceed by putting the formulas. MC delta T of water equals minus M of the cylinder, C of the cylinder, which is that of aluminum, hopefully. I'll just leave it as C to see what we'll get, times delta T of the cylinder. Now I'll substitute So what I want is C of the cylinder. I can rearrange for that. And this is equal to water, C water, delta T water over M cylinder times delta T of the cylinder, and there's a minus sign. The mass of the water is 250. I'm starting with some substitutions. Specific heat of water, in the book, it's not given to you, but in problems. In the exam, it is clearly given to you. In the book, they tell you to always like check the table of constants so they don't have to like write it every single problem. If you check the table of constants, I remember we put it somewhere here. Yeah, here it is. So C of water, I told you we're gonna be using it a lot. As you can see, it is 4186. And that of aluminum is 900, by the way. So we're gonna be checking if we're gonna get 900 in our answer, and then we can tell if this is really aluminum. So this is 4186 times delta T of water is T final minus T initial, which is 25.4, minus T initial, which is 20 for the water. I will divide that by the mass of the cylinder, which is 115, times delta T of the cylinder. T final is 25.4. T initial of the cylinder is 80 degrees. And I will calculate the specific heat of the cylinder. This is equal to, so if you calculate, you will get 900 joules per kilogram Kelvin. And this is indeed for aluminum. So yes, the material is aluminum. The main purpose in calorimetry is always to identify the specific heat of a given solid, and that's what we were doing basically here. So we have here, you draw a 35 liters bath, but at 47 degrees Celsius, it feels too hot. You start adding 9 degrees Celsius water from the cold tap. How much cold water do you need to add to bring the bath to a comfortable 39 degrees Celsius? So we have this hot tub, and it's too hot. It's at 47 degrees Celsius. And we're allowing some cold water at 9 degrees Celsius to flow inside. So the water is going to be coming out, and it is at 9 degrees Celsius here. And the question is, how much water should we add? I want the final temperature to be, so I can draw T final. I want the final temperature to be a comfortable 39 degrees Celsius. Initially, we had here 35 liters. And the question is, we want to add some mass here. We're not sure of the mass of the water, the cold water that we're adding. And our final mixture, pay attention, will contain 35 liters plus the mass of the water that we have added. Again, I'll start as usual with saying that the Q gained equals minus Q lost. This is Q gained by the cold water. Always the cooler object gains energy. This is minus Q lost by the hot tub water. MC delta T. This is M that I have added. T of water, delta T of the cold water equals minus M of the water in the tub, C of water again, delta T of the water in the tub. Notice how both objects are water here. We're mixing the same material, unlike previous problems where we were adding a solid into the water. So it's okay. That makes things easier. Actually, I can cancel out the specific heat, and I will solve for the mass of the water added. This is gonna be minus the mass of the water in the tub, delta T of the tub, over delta T in the tap water. Now, rather than giving me the mass of the water in the bath, I'm giving the volume, but it's okay. Rho is equal to M over V. So M is rho times V. So I'll just put the density of water, which is 1000, times 35. One more issue, this 1000 is kilogram per meter cubed, and this is liters. So I will multiply by 10 power minus 3. This is meters cubed per liter. So I have converted to meters cubed, really. So this will give me 35 kilograms times, and this makes sense, by the way. I don't know if you've noticed, but any bottle of water you buy, let's say you buy the 1.5 liter bottle, its mass is around 1.5 kilograms because the density is just 1000, and you convert that to meters cubed. You divide by 1000 again, so 1 liter ends up to be having a mass of 1 kilogram. Yeah, so delta T of the tub is gonna be 39 minus 47. The final temperature is 39, the initial temperature is 47, and delta T for the tap is 39 minus 9 degrees. So I will calculate this, and you should get 9.3 kilograms, which is 9.3 liters. So I need to add 9.3 liters of cold water in order to bring the tub to a comfortable temperature of 39 degrees Celsius. We have a small part that was added at the end of this problem, which says what happens to the water temperature when a 62 kilogram person enters the tub. Assume the person starts with normal body temperature of 37 degrees Celsius. So what happens here? Again, we're going to be having some lost and gained energy. The person is going to be gaining some energy because he is stepping into a hot tub, right? And how much is he going to be gaining? Again, I can do Q added equals Q lost and solve for the final temperature of the person who is sitting in the tub. So we can solve for the final temperature just as we worked with the rest of the problems, same story all over again. So now I'm gonna be continuing with our formulas for the heat exchanged. We talked before that the amount of heat needed to change the temperature of an object by delta T is Q equals mc delta T, right? This is the formula we discussed. And we said we're going to be using this formula whenever we want to study how much heat is added or removed to an object when its temperature is changing. However, there are certain situations where the temperature doesn't change even when I'm adding heat. Namely, I want you to take a look at the situation of boiling water. You heat up some water in a pot, and this water reaches 100 degrees Celsius. At 100 degrees Celsius, boiling starts. And essentially here, the temperature no longer increases. The temperature remains at 100, and rather than when you continue heating, rather than having the temperature increase, what will happen is boiling will occur, vaporization of the water will be happening, and it will continue to happen. You keep adding heat, you keep the pot on the stove, And what happens instead of an increase in the temperature, you see more vapor being released. So here, what's happening is a phase change. So rather than a temperature change, I have a phase change that is happening here. And a phase change namely occurs when the object reaches its boiling point, or alternatively, it can be reaching its freezing point. So this could be melting, freezing, vaporization, or condensation. So whenever a substance is changing from one phase to another, namely from solid to liquid, or the other way around, from liquid to solid, or from liquid to gas, or from gas to liquid, these are phase changes. In these cases, the temperature becomes fixed and the material starts to change phase. Some of the water will vaporize, vapor will be obtained, a gaseous phase will be obtained, and I keep giving energy until at some point I can vaporize all of the water. So here there's a certain amount of energy that is needed to obtain the phase change. Namely, if I have, let's say, a cup of water and I bring it to boil, I will still need a certain amount of energy to vaporize all of that water. So to vaporize the water, you will need Q equals to M times L. This is the amount of heat needed to completely vaporize a mass M of water. L is another constant as usual because different materials, they need different amounts of energies in order to change their temperature or change their phase. So L is the latent heat. It is a constant that tells me how much different materials need energy to change their phases. I have here some examples of the values of the latent heat. So I want you to notice how the latent heat has bigger orders of magnitude. Look at the latent heat values, 10.8 times 10 power 4, 2 times 10 power 4, 1 times 10 power 4, whereas C was always in the order of 100s. So for example, for aluminum, it was 900. For water, it was 4,186, which was considered quite large. But these are less than the latent heat, which is always like in the order of magnitude of 10,000 and even more, 10 power 5. So the orders of magnitude are more. What does that tell us? Why is L larger than C? And what's the impact of that? This simply tells us that phase change needs more energy than the change in temperature. So if I have water and I'm heating up the water from, let's say, 20 to 100 degrees Celsius, the energy I need is less than when I want to vaporize the water. Changing phase requires a larger magnitude of energy than the temperature change. Of course, it's relative because if you're changing the temperature a lot, like across, I don't know, 1000 Kelvin, that's a lot of temperature change. It will compensate and give you a lot of energy needed. But in real life scenarios where I'm changing the temperature by, let's say, 100K, that's it, then the amount of energy needed is definitely less than that needed for a whole phase change. So I want you to notice something, by the way. Our latent heat values will depend on whether we are going through a phase change from liquid to gas or a phase change from solid to water. So I will distinguish between the latent heat of vaporization and the latent heat of melting. So vaporization is when we are going from liquid to gaseous state or the other way around. I will use the latent heat of vaporization. If we're going from solid to liquid, I will use the latent heat of fusion. Look at the table. So for benzene, let's say, I have the latent heat of fusion here, the latent heat of vaporization here. So I will use according to what phase change I have. If the copper is melting, then I will use the fusion constant. If the copper is vaporizing, I'll use the latent heat of vaporization. And I want you to see if we're going from solid to liquid, then in that case, the material is gaining heat. To go from solid to liquid, we are basically warming up or heating up the material. We are increasing the temperature, and thus we are adding heat. So I will write Q to be equal to plus ml of fusion because we're going through the melting. If we're going from liquid to solid, so the other way around, liquid to solid, I'm freezing some water. So here I'm cooling down, or basically I'm removing heat. So Q is going to be negative minus mLF. Same thing from liquid to gas. I'm going to be adding energy to make some vaporization. For example, when you want to vaporize water, you boil water to vaporize it. And in that case, you are also adding heat. So basically here we have seen two phenomena that would occur when we add heat to a system. Namely, let's say I start with some ice, and I wanted to take a look at all of the processes that would happen when we are warming up the ice. I bring some ice. Let's say I bring 1 kilogram of ice, and initially this ice is at minus 30 degrees Celsius. So it was in some freezer at minus 30. You start adding heat to the ice. Let's say I place it on a pot. The ice starts to warm up. The ice, which is at minus 30, will warm up all the way to 0. So I want you to look at this section. The ice warms up all the way to 0. So the energy involved is the mass of ice times the specific heat of ice times the change of temperature from minus 30 to 0. Now, once the ice reaches 0 degrees Celsius, this is the melting point of ice. So here, T equals 0 degrees Celsius. This is the melting point of ice. So there will be some phase change. And in phase change, Q equals M times L. So the mass of the ice times the latent heat of fusion of water or ice. I'm going to multiply these by each other to calculate the energy needed. I want you to notice something super important. When we have phase change, the temperature doesn't change. So T remains at 0 degrees Celsius. And the graph will be horizontal. I want you to take a look at our graph. This is a temperature versus heat graph. So essentially, if the temperature is changing, you will see the graph like increasing as here or decreasing. But in the phase change, you notice how the temperature is always 0 during the whole melting process. So if you look at our original graph, by the way, you will see sections where the temperature is increasing, then sections where the temperature is constant. Anywhere where the temperature is constant, I will have a phase change occurring so that the temperature doesn't really change. This is a characteristic of phase change only. Here, I have another horizontal line in my graph. This is the boiling of the water. So here, another phase change is happening. So what happened here? We studied the ice warming up to 0 and then melting. All of the ice has melted to water, but I'm keeping it on the stove. So the ice has melted to water, but because I leave it on the stove, the water is gonna warm up as well. So here the water will be warming up. The melted ice will be warming up. It can keep warming up until it reaches the boiling point. So I heat it up, it reaches 100 degrees Celsius. The amount of energy involved in this heating is given here, mc delta T again, but for water now, not for the ice. Now at 100 degrees Celsius, the water will boil. And when the water boils, it will essentially do some phase change. So we will have some energy involved in the phase change. For the vaporization, Q is equal to the mass of the water times the latent heat of vaporization. So you can find the amount of heat needed for the vaporization, and the vaporization is essentially occurring here in this section. The temperature remains constant. Now let's say all of the water vaporizes, then the water becomes water vapor, right? And this water vapor, it will be at 100 degrees Celsius as well. And if I heat it even more, then the water vapor will also warm up. And here I'll put the energy Q involved. It will be the mass of the vapor, C of water vapor, times delta T. But notice how here there's no more phase change to occur. You can just increase the temperature infinitely to heat up your water vapor more and more. So our graph has sections which have moved and transformed ice at minus 30 degrees Celsius all the way to water vapor at some given final temperature. Sometimes we don't really study all the way from ice to vapor. Sometimes I tell you I warmed up the ice and I melted half of it. This means we have stopped somewhere here. Like I can stop here. Then all of the Q involved is gonna be M ice, C ice, delta T plus ML. But here this is M prime L, not all of the ice. Like I have, let's say, melted half of it. So this is namely the mass of the ice over 2. And I can check the energy needed to warm up all of the ice to 0 and melt half of it. You will be given different scenarios to discuss. They would correspond to different parts of this graph. You can see here I will put for you some numerical values. I have 1 gram of a substance. If I change the temperature from minus 30 to 0, so same scenario, but we have some numerical values. Q will be mc delta T. C is the specific heat of ice, not water. Pay attention. The specific heat of water is different from that of ice, by the way. C of ice is 2090. C of water is 4186. So if I have ice at minus 30, this will warm up we will use the specific heat of 2090 of ice to find how much energy is needed to warm it up. So I warm it up to 0. Q will be mc delta T. I have 1 gram of ice, so this is 10 power minus 3 kilograms. C is 2090, and delta T is our final temperature, which is 0 degrees Celsius here. So here Q was C times the mass times delta T. C is 2090. The mass is 1 gram times 10 power minus 3. This becomes kilograms. Delta T is 0 minus minus 30. This becomes plus 30 as you can see here. And the final energy needed to heat up all of the ice from minus 30 to 0 is 63 joules. Then at 0 degrees Celsius, the ice-water mixture remains at constant temperature until all of the ice melts. So for the melting, for the phase change, I will have Q is equal to ml, where m is the mass, which is 1 gram, and L is the latent heat of fusion or melting. This is given in the table. It is 3.33 times 10 power 5. You find the amount of energy needed. It is 333 joules to melt all of the ice. Now I can study between 0, like after all of the ice has melted, it has become liquid water. I keep heating up. The water will start warming up across section C here, all the way until it reaches the boiling point of 100 degrees Celsius. Between 0 and 100 degrees Celsius, no phase change occurs. The energy added is used to increase the temperature of the water. The amount of energy needed to increase the temperature of water is Q equals mc delta T, where m is the mass of the water, C is the specific heat of the water, which is 4186, and delta T is gonna be 100 minus 0. The initial temperature is 0, the final temperature is 100. So we found Q for warming up the water from 0 to 100 degrees Celsius is going to be 419 joules. Now, once we reach 100 degrees Celsius, there is a phase change. The water boils. This is section D, where you notice it's a horizontal line, no temperature change here. We have a phase change. And this is a phase change from water to vapor. In that case, I will use Q equals ml, the mass of the water, times the latent heat of vaporization. It's a different constant from the melting, by the way. It is 2.26 times 10 power 6. For melting, I used 3.33 times 10 power 5. Remember, in the table of constants, I have a latent heat for fusion or melting and a latent heat for vaporization or condensation. We find the Q for the phase change from water to steam, and this amount of energy is needed, 2.26 times 10 power 3 joules. What we obtain is some vapor. Here in section E, all of the water has vaporized into steam. I can also keep raising the temperature of the steam. Let's say the final temperature was 120, like we stop here. The final temperature of the system is 120. So there will be some additional amount of energy involved. Namely, this is the energy involved when we want to increase the temperature of the steam from 100 degrees Celsius to the final temperature of 120. And then Q is going to be equal to mc delta T again. But C is the specific heat of water vapor, which we also name as steam. And this is actually equal to 2010. So we substitute that. Delta T is the final temperature, which is 120, minus the initial temperature of the steam, which is 100 degrees Celsius. And then I can find the total energy needed to convert 1 gram of ice at minus 30 degrees Celsius to steam at 100 degrees Celsius. And this is going to be the sum of all of the energies we found for each section. This is the total energy needed to go all the way from ice to steam. Let's check some example that we can solve. So, how much heat must be absorbed by ice of mass 720 grams at T initial equal minus 10 degrees Celsius to take it to a liquid state at 15 degrees Celsius? So here I want you, whenever we are heating up a certain material, I want you to first look at the processes happening. Step 1, identify processes. The processes will be some warming and some phase change if there is any. So identify what's happening. Initially, I had ice at minus 10 degrees Celsius. And finally, my final mixture should be water at 15 degrees Celsius. To go from ice at minus 10 to water at 15, I will need to warm up the ice until it reaches its maximum possible temperature, which is at 0 degrees Celsius. At 0, it will turn into water at 0 degrees Celsius. So here the amount of energy is ml really. Here to go from ice at minus 10 to ice at 0, Q is mc delta T, where C is for ice. And finally, when I convert all of the ice to water with using an energy ml, the water should also heat up to 15 degrees Celsius. So here I have Q equals mc delta T of water. So you can see now in front of you, for the different processes, the energy needed for each one. So step 2 would be find the energy for each process to occur and deduce the total energy. Q total is going to be equal to Q ice plus Q of phase change. So here ice warming, that's process 1, plus Q of the phase change, plus Q of water warming. So these are the 3 processes I have drawn in my figure. This will be M, C of ice, delta T of ice, plus ML, plus M of the water, C of the water, delta T of the water. Now the mass is the same everywhere because it's the same amount of ice, all converted to liquid. So I can take that as a common, and this will be 0.72 kilograms. T of ice is usually given to us. It's 2220. Delta T of ice. So ice was at minus 10. It became at 0. So this is 0 minus minus 10. Plus the latent heat for the phase change. We have melting here. So I will study the latent heat of fusion, which is 333 kilojoule per kilogram. So this is a 333 times 10 power 3 plus C of water 4186 times delta T of water, which is 15 minus 0. The final temperature of the water is 15. The initial temperature of the water is 0 due to the phase change. You calculate, you add all of these up, you get the final total energy needed. It's going to be 300,000 joules. So in part B, things become harder. We're told if we supply the ice with a total energy of only 210 kilojoule as heat, what are the final state and temperature of the water? So rather than giving the needed energy of 300,000 joules to take the ice at minus 10 all the way to water at 15, we only gave a less amount of heat, and we want to guess what's the final mixture that we will get. So is all of the ice gonna be melting to water and then the water heats up a little bit to less than 15, or is the water gonna be melting halfway and some of the ice will remain ice? What's going on? So what I'm gonna do here to know how much this energy would allow me to go, I'm gonna check Q needed for the ice to heat up to 0. This alone, I calculated, it's the mass of the ice times C times delta T. It is equal to 15.9 kilojoules. The energy we gave is 210. So this energy is sufficient to at least heat up all of the ice. Now to melt the ice, I will need Q2 equal ml, which is around 240 kilojoule. I gave 210 only, and some of that will go to warm up the ice. I need to subtract 16 kilojoule from that. So what will remain is 194, and what I need to melt all of the ice is 240. So this energy, you can now guess, it will help in heating up the ice from -10 to 0, and then it will do some melting, but the melting will not be complete because the energy is not sufficient. Some of the ice will remain there. I will have partial melting. What is the question? What are the final state and temperature of the water? Well, the final state is going to be a mixture of partial melting and partial amount of ice remaining. The temperature will definitely be 0 because at phase change, the ice is at 0 and is converted to water at 0. Both will remain at 0 until melting is complete. If the melting is complete and I add up more energy, then the water can warm up. But here the melting is not complete, so my mixture will remain at 0 degree Celsius. So part C. If we add only 210 kilojoule of heat, the ice partially melts, as we have seen before. Find how much of the ice melts. Because we said there's partial melting, this means that some of the ice will melt. So some of that mass, which was initially 720 grams, will be melting and some will remain as ice. I want to see how much melts. So one thing is, notice you are given a Q. It is 210 kilojoules. And the Q is going to be M of the ice, C ice, delta T, plus ML. But the mass here is not the total mass of the ice. I'll name it M melted, the mass that has melted, and I can easily solve for that. It is going to be 210 kilojoule minus the mass of the ice, C ice, delta T. Remember, the ice warms up from -15 to 0, so I will need MC delta T of energy to heat it up to 0. And then the melting will occur. So I need to account for both energies, and I will divide by the latent heat here to solve for the melted mass. I'll have 210 times 10 power 3 times the mass of ice was 720. I'll multiply by 10 power minus 3 so that this becomes in kilograms. C of ice is 220. This is given to you. The temperature change is 0 minus 10. The initial temperature was -10. And the latent heat is 333 times 10 power 3. I can calculate the mass that melts. This is going to be 0.58 kilograms. The initial mass was 720 grams. So 580 grams melt, and well, 140 grams remains as ice. We obtain a mixture of both ice and water. The temperature, final temperature, is 0 degrees Celsius because we stopped in the middle of phase change where the temperature doesn't change. And it's essentially equal to the temperature of the boiling point that we had here, or the melting point.